Okay, we're just going to do some review of some of the big ideas that we've learned so far. So, distance time graphs. So we saw these that we can actually look at a distance time graph and see what the speed is, because speed is distance over time. So we know that that is the formula for speed. And if you ever forget, you can just think about a speed, like if you're going 100 kilometers per hour, you're basically taking the kilometers and dividing it by an hour, so kilometers per hour. And what we saw was that because in a distance time graph, this is y and this is x, it's the same thing as having like the change in y, the change in the distance, divided by the change in x, the change in the time. So it's an equivalent way of writing that. So what it means, it tells us, is that when we're looking at a graph, the steeper the slope, the higher the speed, if we're looking at a distance time graph. And so we can calculate the speed of any segment. There's a chart here for us. So we can see in A, if we're looking at segment A here, the distance traveled is 250 meters, and that takes 3 minutes. So the speed, which is distance over time here to find speed, we're taking the distance of 250 meters and dividing it by 3 minutes, which gives us, if we do 250 divided by 3, we get 83.3 meters per minute. And the direction is away from home, because she's getting, if 0 is her home, then she's getting farther away. Okay, so let's look at what's happening in section B. So in section B, we're starting here at 250, and then we're going down here. So we need to figure out what is the distance. So first, it would be helpful to know what each of these squares is. So it looks like it is 25. It's going up by 25s. So if I want to count how far this is here, this is 25, 50, 75, 100. So she has gone 100 meters. And how long does that take her? Well, we can see these are going up by 1. So 1, 2, 3, 4 minutes. So for our distance divided by time, which is 100 divided by 4, we would have 25, and it's a good idea to put in your units here so that you know what your units will be at the end, meters per minute. And we can see here she's going back towards her home. She's going the opposite direction. Section C. So we're starting here and going to here. There is no distance traveled here. It's a horizontal line. And we can't figure out how long they were there though. So we can count 1, 2, 3, 4, 5, 5 minutes. And speed is 0 because they weren't moving. And we can write that they were stopped. Okay, the last section there is section D. So section D starts here and goes here. So we can see that they started at 150 meters away and then they went back to 0. So distance traveled is 150 meters. This took them 1, 2, 3, 4, 5, 6, 7 minutes. So if we're doing distance divided by time, we're going to do 150 meters divided by 7 minutes, which gives about 21.4 meters per minute. And again, she's walking towards home. Okay, so the next concept that I wanted to take a look at was the different words that we use for slope. So if you remember, the very first word that we used when we were talking about patterns was the multiplier. And so we saw that when we were looking at physical patterns, and when we were looking at tables, it was the amount that it increased by each time, or the number that we're multiplying by. Input then we take the input and multiply it by the multiplier. And then when we started to look at graphs, we started using this word of slope because we saw that the bigger the multiplier, the steeper the slope of the line. And the other word that we've been using, or the other term, is rate of change, which makes sense, particularly in word situations, like if you have the rate at which people are crossing the stage, or the rate at which your bank account is changing. So in a lot of these situations, or all these situations, the multiplier is some type of rate. And then kind of the way that we've been calculating these, the main one that we've been using is change in y divided by change in x. We're always taking the y value, the dependent variable, and dividing it by the x value, which is the independent variable. But some other versions of this that we've seen are, instead of change in y, we can use the word rise, and instead of change of x, we can use the word run, which is basically what we're doing up here, right? When we were counting these right here, that was like counting the rise. And then when we were counting across for the change in x, or the change in time, that's like the run. So it's just different terms for the same thing. And so then lastly is that speed application that we just saw of distance over time. Different words for y-intercept that we've been using. We started with talking about the constant, because we saw that at position 0, that was the constant, or the other way we were looking at it was that the constant stayed the same in the pattern, like it was the part of the pattern that stayed the same, so it was constant. And then when we saw the graph, it made sense to call that the y-intercept, because on a graph, at position 0 is on the y-axis. So wherever that is crossing the y-axis, that is your y-intercept, or your constant. And then in context, it makes sense to talk about the initial value, because it's where you're starting at, your starting point. So things like they started with $100 in their bank account, and then it decreased by $30 a week. So the initial value would be the $100. And just another reminder about that in a table, the constant, or the y-intercept, is always happening at position 0. So that's how we can find it in a table. So let's take a look at this example right here. We have that a class measures the diameter of a snowball as it melts, and information about the diameter at 2 different times is shown. So it asks us how long will it take for the snowball to melt completely, which we'll answer that in a few minutes. But let's write the equation of this line to get some practice with that. So we can see here that we're actually lucky because we have the constant right there, the y-intercept. So we know that the constant, or when we write this equation, we're going to have plus 24 there. And then if we want to find the multiplier, we could use rise over run, just to give you an example to review that. So rise over run, remember, we're just looking to see what is the rise, or the change in y here. And so we can see these squares are all going up by 2. So this actually went down 4. So the rise is -4. And then we want to figure out what the run is, which really is just the change in the x values. These are going up by 1, so we have 1, 2, 3, 4, 5. So the run is 5. So if we wanted to do rise over run, use that version, we could do that. We have -4 over 5, which is -0.8. Many of you like to organize in a table first, which is totally fine. If you did that, if you did a table here, you would have the points 0, 24, and the other point is 5, 20. And so then you would just be finding the change in y, which is -4, and the change in x, which is 5, which we're seeing here, right? Change in y, or rise, is -4, and then change in x is 5. So we know that our multiplier is -0.8. So we're going to have -0.8x plus 24. So the question here is actually how long will it take for the snowball to melt completely? So what that means is how long until it has a diameter of 0. And so we could use the graph and kind of extend that. We can see that this is actually, this line, even if it was a straight line, not just my freehand line, it would be off the graph. So you could try to make a good estimate, but it's probably better to use our equation here. So if we use our equation to find out when is y 0, when is the diameter 0, we can write it like this. And let's just solve this equation to try to get x by itself. So the first thing I'm going to do is get rid of this 24. So I'll have negative 24 equals negative 0.8x. And then to get rid of the negative 0.8, I'm going to divide that on both sides. So we have, I'm going to have a positive number, and negative divided by negative is a positive, and 24 divided by 0.8 gives us 30. So that tells us then that it will be 30 minutes. It'll take 30 minutes for it to melt completely to get a y value of 0. Okay, so lastly, I just wanted to review some of the algebra that we've been doing. So we talked about the distributive property and how we can get rid of these brackets. So we can multiply this value in to both of these. And I'm not going to explain why right now. You can go back to the original video to go over that again for more details. But this is kind of the ending conclusion on how we simplify this. So we'd actually have negative 3 times x, which is negative 3x. And negative 3 times negative 2 is plus 6. And then remember that if you just have a negative, like this one right here, it makes everything in the brackets the opposite. Or the other way of thinking of that is it's like kind of like a negative 1 that we're multiplying in. So we have negative x and negative 5. And then this last term we have 2 times x squared and 2 times negative 3x, which would be negative 3x squared. Sorry, 2 times negative 3x would be negative 6x squared. Negative 6x. Woo. Sorry, guys. Truth be told, I just did this video before and the sound did not work, so now this is time 2. But these things happen with technology. Okay, so negative 3x minus x minus 6x. Remember, we can combine the like terms. So negative 3 minus 1 is negative 4. And then negative 4 minus 6 gives us negative 10x. And then, is there anything else we can combine? Oh, we have here a 6 and a minus 5, so we can combine that. And then this last one, we don't have any other x squared terms. We cannot combine it with the x's because they're not the same. So we have plus 2x squared. So you could just leave it like this if you wanted, or kind of the proper way, or the textbook way, is to write your exponents in descending order. So either of those would be correct. Okay, solving equations with variables on both sides. So let's just go over that. So remember, the first step is that you should try to simplify or get rid of any brackets. So we see we have brackets here. We need to use the distributive property for those. So 2 times x is 2x, and 2 times negative 2 is minus 4. And there's nothing else I can simplify. So now the big strategy is to get variables on the one side and all the numbers on the other. It's kind of our main strategy here. So it doesn't matter which side, but I want to get all the x's on one side and all the numbers on the other. So I'm going to put the x's over on this side. Doesn't matter really. So I'm going to get rid of this 3x minus 3x, and then I have to subtract 3x over here too to keep it balanced. So 2x minus 3x gives me negative 1x, or negative x. I still have minus 4 here. And then that equals negative 14. Okay, so I need to get all the numbers on the other side. So I want to get rid of this negative 4. I'm going to add 4 to both sides. So I'm left with negative x equals negative 10. And then if you're ever in this case where you have like a negative x, it's just like a negative 1 here. So we can, to get rid of it, we can divide both sides by negative 1. So we have x equals 10. And that's our solution. All right, thank you for watching.